Okay, I'll start lecture 25, and this is on Monte Carlo simulation applications. In lecture number 24 yesterday, I looked at the Godiva problem and went through the details of making the input file and how to read the output file and to understand everything properly. So today I'll take you through another very interesting experiment. Now these are the things that you learn when you are doing your master's or PhD. Whenever you begin your PhD, then if you're simulating any big nuclear system, so these are the kind of problems that you should begin with, and that's what I recommend, and that's what I've always done. So you should always have your feet on the ground and of course head above the clouds. So let's look at Clark's criticality experiment. Now these are all basic experiments which were carried out in the 60s and 70s. And there was a lot of work done at the national labs in America. And we are fortunate to have data of those experiments for the benefit of everybody, everywhere, to get knowledge. So this is a paper, the reference is Clark 1966, and effect of distribution of fissile material on critical mass, Nuclear Science and Engineering, volume 24, number 2, pages 133 to 141. And I've made an input file in Clark A19. And if you're looking from the top, then these are the 5 cylinders. They're separated by sheets of aluminum. And this is a critical system, so the K is about 1. Okay, now in this, what Clark's paper does is that he looks at the influence of non-uniform distribution of the fissile actinides, U235, plutonium-239, and uranium-233. So it's a homogeneous mixture, and there is a very interesting concept called the minimum critical mass. That, of course, you know, we were taught that critical mass is the minimum amount of mass that you need to sustain a chain reaction. But even within the possible critical masses, there is a further minimum which comes about by non-uniform distribution. And it was Goetzel who derived an expression for the fissile fuel distribution, which gives you the minimum critical mass. And he said that this gives you a flat thermal flux. So he showed that in a 2-group formulation, diffusion, for a reflected reactor. This is also reflected with water, and it's just a homogeneous solution of U235 in water, the case that I'm considering with you. Clark has done plutonium-239 and uranium-233 and has covered more in the paper. But my interest specifically is on the criticality of this in this experiment and of how you can study non-uniform distribution so that you can see that how low can you go in terms of mass to achieve critical mass. So let me read this, his abstract. The influence of the distribution of U235, plutonium-239, and uranium-233 in water on the minimum critical mass, the minimum critical concentration per unit length of cylinder, and the minimum critical mass per unit area of slab surface is calculated. 2 energy groups are employed, this is by Clark, in the calculations with parameters normalized to force agreement between calculations and experiments performed with water reflected spheres containing uniform aqueous solutions having a wide range of concentrations. So just like you put salt or sugar in a glass of water, so we're putting uranium in a glass of water. So calculations made by Clark with these parameters for a water reflected cylinder in which the optimum distribution for minimum mass was approximated with 5 coaxial regions, which I just showed you, They agree well with experimental results. Now, the minimum critical masses that Clark found, minimum critical mass was for 235, 768 grams. So imagine, I just told you that for Godiva, it's about a 50 kilogram sphere. And now I'm telling you that the minimum critical mass is 768 grams, so less than a kilogram. And now, why is this so important? Because when you're storing uranium solutions, plutonium solutions in nuclear facilities, then they can lead to an accident. And that's called a criticality accident. And somebody can die then. So you can have a burst of energy. So it's very important for you to know what is the lower limit for safety. Okay, so this is the minimum critical mass, and this is the concentration per unit length of cylinder, 16.9 grams per centimeter, and this is the mass per unit area, which is 0.417 grams per centimeter square. These numbers are for plutonium, and these numbers are for U-233. Okay. Now, in the reference experiment that Clark did, you can see over here that these are 5 coaxial cylinders with different volumes, so they're not equal volume, and they've got so much mass of solution in them. So the mass of U-235 is distributed like this. So you've got less over here and more over here, but because you've got more volume, so the concentration is 39.79 grams of U-235 per liter in each of those 5. Okay? And let's call this the reference configuration. So in the reference configuration, the numbers that you see are over here, that in the 5 regions, the inner radius, for example, the first region goes from 0 to 5.48. The second goes from 5.54 to 8.08. So between this and this, there's the thickness of the divider. So here the thickness is that much, here the thickness is that much, and here the thickness. So this is the first region, second region, third region, fourth region, and fifth region. Now, the grams of U-235 per liter are this much. Okay. Now, so what you can see is that the number density of U-235 divided by the reference density, it's more over here than this. Okay, previously it was equal, and okay, so here the masses that you see are that you've got more inside. So inside you've got 269 grams, outside you've got 143 grams. So now the number density that you have over here is about equal. Okay. Now this is the optimal distribution that you see over here. The optimal distribution comes by adding 100 grams in the first region, 60 grams in the second, 5 in the third, and by removing material from the outer regions. So that's what has happened over here. So first you see that there was more mass going out, and here you've got the opposite over here. So instead of 160, you've got about 270. So you've added about 100, between 100 and 110 grams. Now, when you have this kind of a distribution, you reduce the mass in this particular configuration. So you reduce the mass from 1170 grams, which you had in the reference case, down to 1048.8 grams. Now, that is just by distributing the fuel like this. So, so again, in pictures over here, these are these 5 regions, 1, 2, 3, 4, and 5. So first you had equal concentration, grams per liter. Now you do not have equal concentration. Now you've put more in the first you put 60 in this, you put 100 more grams in the first. So you took out from this region and this region and transferred it in here, because the importance is more over here. So now this is the physical significance of importance, that, and this is what Goetzel said, that if you have a non-uniform distribution, if you shuffle your fuel in such a way that you produce a flat thermal flux in a reflected system, then you can reduce the critical mass. And if you go on doing this, then you come to what is called the minimum critical mass. So this is a very important concept that we've all got to learn, that with a critical mass, there is also a minimum critical mass. Now, I find this fascinating. And so what I did was to first carry out a Monte Carlo simulation of the reference, and then to sample derivatives. And when you sample derivatives, then in a single run, you can make predictions. And so you can make predictions to find out the sensitivity of each of these volumetric regions, and you can then obtain an optimal distribution. Now, let's see that what does adding more in the first region, what does that result in for the thermal flux? So here I plotted the radius of the cylinder going from 0 to 15 point something. And you can see that with a uniform distribution of 39.79, this is what the thermal flux was looking like. You know that it comes down, then there's a hump over here in the reflector, and it comes down like that. So when we distributed the fuel, then what you can see, this solid curve over here, that the thermal flux was suppressed over here and it was enhanced over here. So you can see a flattening of the thermal flux. Now, this is the theory that in a reflected system, if you can produce a thermal flux, then you can get minimum critical mass. Now, from a reactor point of view, it means that you have to have non-uniform fuel distribution. And so this is a very powerful theory in nuclear engineering. And this is what I studied, and I've got an MCNP input file and output file, and got some research papers on this also. But this is research where you'll find lots of papers, earlier papers in nuclear science and engineering, and then you'll find a paper in Annals of Nuclear Energy. You'll find papers by Goetzel, Williams, Lewins, Van Dam, and and the earlier names of NSE of the 70s. So this is a lot of research and something very interesting. Okay, now let's come to a reflected system. Now this system I've taken from Lamarche, the book Introduction to Nuclear Reactor Theory, page 336. And I'm also going to show you results in this connection from two other papers. One paper is by Wright and Hooper, and it's 2008, Nuclear Science and Engineering, and it says calculation of the minimum critical mass of fissile nuclides. Okay, so let me take a bare sphere of a homogeneous mixture of U235 and water, and let me reflect it with an outer sphere of water. So the inner sphere is core, the outer is reflected. Now, in the book by Lamarche, this is the data for the two-group analysis which has been carried out. You can go to page 336 and you can see how the two-group theory is built in. So there are two-group equations, one for the fast group and one for the thermal group. So there are two equations in the core and two in the reflector. Now, the two equations, second order, ODEs in coupled ODEs in the core, you convert it into 1/4 order. When you convert it into 1/4 order, you get two roots, you get mu and lambda. So this is that mu and that's the lambda. And then you can write it in terms of functions. In spherical geometry, it's sine and sine hyperbolic. In cylindrical geometry, it is Bessel functions. In slab geometry, it is trig functions. So, okay. So if you do this, so keep the water to fissile ratio as 500. Now, one water has two hydrogens, right? So if the W over H is 500, so one W has two H's. So you can see that that's the hydrogen to U235 ratio from there. Now the results in Lamarche are written here, that he gets a two-group result of 21.9 centimeters for the critical radius of the core, and the thickness of the reflector he gets as, I think it's 18.1 centimeters. You can check the book. And so this adds up to about 40 centimeters. The K effective for Lamarche, it's understood to be 1 because that is where the determinant of the 4 by 4 matrix goes to 0. Because they use Kramer's rule where the homogeneous equations, the only solution they've got is when the determinant goes to 0. So in Lamarche, this is the result. Now I did the same thing with Monte Carlo simulation. I get slightly different results. I get 22.5 centimeters for the radius, critical radius of the core, as compared with 21.9 that Lamarche gets. So you can see that there is some difference between diffusion and Monte Carlo, and of course this is better. And the reflector thickness is 22.5 centimeters, so this is 45 centimeters. The K effective I get is 1.00244. You can change this a little bit and come down to 1, so you can try that. But this is what I get. And then what I did was that, so Lamarche results are here, 21.9 centimeters radius, reflector, K. And Lamarche says that with 1.15 kg or 1150 grams of U235, you get criticality for a uniform case. Then my results for with MCNP give me a K value shown here with standard error, relative error less than 1%, so it's about 0.11%, and the mass I get is 1247.7 grams. So Monte Carlo says that a uniform distribution requires a critical mass of 1247.7 grams of U235. Okay, then I did two other things. I tried to get a distribution using the Gertzel's distribution and to get a flat thermal flux in a spherical system. Now, when I did that, then see, this is what happens to the core. It becomes smaller in size. And when it becomes smaller in size and the reflector is the same, so how much mass, and this is the K value, so I can do it with 702, 703 grams. Now, there's a theory that you need to have a delta source at the end for continuity. Otherwise, you get a discontinuity in the current. So then I did some work on flat thermal flux with a delta source. And this is what I get. You can verify this yourself, but these are my results, and they're not published anywhere. So I've sent it for publication. So this is the result that I get, that with 718 grams, you can have criticality. Now, what does Clark say? Remember, we had a number from Clark on U235. So the number from Clark that we had was 768 grams. Okay, now I don't know which geometry that was in, but here I'm getting 718 grams. Okay, so this is also very interesting. You can do all these verifications yourself. Now let's look at some papers on these estimates. Now this is a paper which I want to show you. This is a mass estimates of very small reactor cores fueled by U235, U233, and CM245. This is a report by Wright and Lipinski, and it's a Sandia report, quite an old report, but look at the results. Now, the results are that on the x-axis, you see the concentration in kilograms per liter. Now the concentration that I showed you was, I think, 1 kg in 44 liters. So it's 1000 divided by, so it's about 27. The one that I showed you was about 0.027 kilograms per liter. Okay, so 1 divided by 44 is how much? It's, I think, somewhere over here. So I showed you the result over here just now for the bare U235 sphere, and I was getting about 700 grams. So by this curve, it looks right. But this paper says that if you come further down to this number over here, which is 0.02, 03, 04, let's say 0.05. So this says that if you come down to 50 kilograms per liter, so you get about, that's 9, 8, 7, you get about slightly more than 700. Okay, so I could improve it a little bit. So here what you can see is that the y-axis over here shows the solid curve is the mass of, critical mass of U235 in the concentration. The others are the system and the total. So this is the curve that we need to look at, this one. So you can see that after a certain concentration, the critical mass begins to rise because of leakage, because of competing effects of fission and leakage. So obviously, there is some point over here which you need to search for. Okay, let's read the caption over here. It says, Figure 1, critical mass and system masses for spheres of homogeneous, water moderated, and water reflected. So there's a reflector over here also of U235 solutions. Red solid curve shows the critical mass. The dotted curve shows the estimates of the solution plus of the solution mass plus the 25 millimeter water reflector. The black dashed curve at the top shows the total system mass, including a 1 centimeter thick nickel alloy containment with average density of 8 kilograms per liter. So I would say this is a very, very useful figure for you. And if you are in the business of safety, if you are in the business of storage, then this is the number that you should be interested in, that what is the most dangerous, the smallest safety limit which I should avoid. You know, many times people say that, oh, the criticality is kilograms. Now, having worked in one of those kind of establishments myself, I know that sometimes people are careless. And so the person who's well-read, who knows the theory, can always help save lives and help enforce safety. Because the more aware you are, the more safety conscious you are. And in engineering, the most important thing is safety. There's nothing more important than safety. The safety of the people who work. Okay, so that's one paper that I wanted to show you. Now let's come to the second paper, which is calculation of the minimum critical mass of fissile nuclides. Now this is by Wright and Hopper, and it's an Oak Ridge National Lab contribution. And they have a model called the OB1 model. Now you know that actinides, if I remember right, actinide is something which has an atomic number 98 going up to 103, and there are 15 actinides beginning from actinium going to lawrencium, I think, if I'm right. And out of those 15 actinides, some are fissile, like U235, plutonium-239. So these are, and so apart from uranium and plutonium, of course, these are all of interest to find out what is the minimum critical mass. And look over here that some numbers are pretty scary, they're very low. So in solution, so this is a very good contribution, this report by Wright and Hopper. And you can see that now these are all numbers that as a student, I think you should, if you can get cross sections of these materials, you should know the safety of all of these things. Okay, so that ends this lecture. So this lecture was on Clark's experiment, criticality experiment, and in the 5 regions. Okay, and so that's what it was. Okay, well, I think we've only done 25 minutes. So let me continue this lecture. Okay, so let me, I have not planned to go ahead, but let me begin lecture 26. Okay, so now lecture 26 is on a bare cylindrical reactor. So it's a continuation now. And here I'm going to show you a paper by, okay, so these are the things that I'm going to teach over here. It's a cylindrical homogeneous reactor. Okay. And this is one of the earlier Westinghouse designs, which was set up in Korea. This is a Korean paper by Chang-Kun Lee. And critical mass minimization of a cylindrical geometry reactor, a cylindrical geometry reactor by two-group diffusion. So notice in those days they were doing two-group and using it for practical problems. And this paper was published in Nuclear Engineering and Technology, Volume 5, Number 2, Korean Nuclear Society. And it's a homogeneous solution U235 and water. Now let's read the abstract of this paper. Abstract is that Pontryagin's maximum principle is applied to the minimum critical mass problem without any restriction on the ranges of uranium enrichment. Now remember, in those days, there were low enrichment reactors. So this is a reactor which gets critical at about 1.1% enrichment. Of course, these days you have 3%, 4% PWRs. So for the analysis that Lee used, a two-group diffusion equation was used for a cylindrical reactor, neglecting the vertical axis consideration. The result shows that the three-zone reactor turns out to be most optimal. Now, what they're trying over here is, again, a non-uniform distribution, an optimal distribution, and see what they get. That they said that if your inner and outer zones have minimum enrichment, whereas the middle zone has the maximum enrichment, then they get a reactor of minimum critical mass. Okay. And they say that you get computed values. It is found from many, okay, let's read this. The result shows that the three-zone reactor turns out to be the most optimal. The inner and outer zones with the minimum enrichment, whereas the middle zone with the maximum enrichment. Now with the given three-zoned reactor, the critical condition is derived. Now that is the determinant that I showed you by applying boundary conditions in two-group theory. And I told you that there's a Kramer's rule. So when you have a homogeneous system of linear equations, you cannot solve them by doing AX equal to B. So what you have to do is that you have to use Kramer's rule, where the determinant is zero. So either you're given the composition and you find the dimension of the reactor, or you're given the dimension and find the composition at which it is critical. But that is called the critical determinant. So that is used in Lamarche, and that is used in this paper as well, two-group. Lamarche used it for a spherical system, and Lee is using it for a cylindrical system. So by finding the roots of the determinant, the numerical calculation of the minimum critical mass is carried out for the case of the Korean Kori reactor, geometry changing the minimum or the maximum enrichment. It is found from many computed values that the least possible critical mass turns out to be the case of 1.2% enrichment for the maximum for the middle zone, and 0.65%. Notice this is less than 0.71, so it's a kind of depleted uranium. So 0.65% minimum enrichment for the inner and outer zones. Okay, so what I did was that I have an input file over here, Lee valid. Those of you who are interested, I can mail it to you and you can do a run of this. Now, this is a PhD thesis by Hamda Khan, and she did research on this, and she's going to do her own recordings on the optimization part of it. But this is just to give you a summary from the applications point of view. So if you run a full simulation for a one group homogeneous reactor, then you get enrichment of, I get 1.09%, and it has 518.6 kilograms of U235 and 47,223.2 kilograms of U235 in water. So this is water. Okay, this is what the reactor looks like. It's a cylinder of height. You can see from here, the height is about less than 300 centimeters, so less than 3 meters. I think it's about 2.7 meters. And if you look at the diameter, then the diameter is, I'll just show you, I think it's, I forget, here it's, okay, here's the diameter. It's about 120 centimeters is the radius. So the diameter is about 2.4 meters, and the height is about 2.7 meters. And you know, there's a very special thing about those cylinders whose height and diameter are equal, and they're called, that's the case of minimum volume. And you can show by differentiation that that is the turning point. So we'll do that in an optimization problem where you can show that given the surface area of a cylinder, what is the minimum volume, and it is, that's the case that you get. Okay, so here the summary of this from a nuclear engineering point of view is that 47.7 tons of uranium is the fuel, 47.7 tons, out of which about half a ton is U235. Now in those days, even half a ton of U235 must have been quite a task to get. This is 60s and 70s that we're talking about. Okay, so now in the study that my student did in her PhD was this, that she took, instead of one cylinder, she made it into a two zone and a three zone, like Lee did using two group diffusion. So in this paper, which is published, I think in NTRP, so we'll have more on that later, but this is a two zone thing. And here again, the idea is to use Monte Carlo perturbation theory. So this is a two zone reactor, and these are Lee's results that you can see. Now we get slightly different results from Lee's results, but do try to verify them when you get a chance. So basically what Lee found are combinations. Now this is Pontryagin's maximum principle. So in case you don't know that, I'll have one of my future lectures on optimal control. And that's also an area which you need to know when you're doing optimization of nuclear systems. In optimal analysis, there are essentially two things that you can do. One is you can do a continuous analysis. The second is what you discrete or bang-bang or Pontryagin maximum principle. So in Pontryagin maximum principle, you assume discrete values for the control variable. So he's got U min and U max. So he said that you've got U min in the inner and outer regions and U max in the central region. So you can see that, okay, we've got two y-axis. Let's see what the y-axis is. So the x-axis is the U max. So this is the maximum enrichment in the central region. And where's the U min? It's on this y-axis. Okay, so here's U min and here's U max. And this solid curve that you see are the combinations of U min and U max. And at each of these combinations, the reactor is critical, which means that you can run a reactor 1.2, 0.65. You can run a reactor 1.1, 0.71. You can run a reactor 1% enriched in the center and 0.8% enriched on the two sides. So 1, 2, 3, 4, 5, 6, 7. He's given 7 combinations of U min and U max enrichment values at which the Koreshi reactor is critical, according to them, in a two-group analysis. And these are percentage enrichments. Now the upper curve, the dashed curve, is for the right side of the y-axis, which is the relative critical mass. So what they're saying is that the relative critical mass is minimum. It shows a minimum. So if you go this side, it goes up. If you go this side, it goes up. Okay. So it goes up on either side. Now, what does that mean? That means that what they showed over here is that, first of all, they looked at a one zone problem, then two zone, then three zone, then four zone, and so many zones. And so they showed the figure of the, the function where, for which you used a maximum and minimum. So bang control says that you use a certain value, and the maximum principle says that the maximum value of the Hamiltonian should be for that combination for which either a maximization problem or a minimization problem. It's a very long story. I think I need to have a full lecture of that. But for the time being, just say that these control variables are discretized. These are all the critical pairs. And one of these, you see now minimization is the negative of a maximization problem. So you can use Pontryagin maximum principle, just multiply the objective function with the negative sign. And the rest of the analysis is all the same, that you use the Lagrange multipliers, which become your adjoint equations. So here you have to solve your forward equations and your adjoint equations. Now this is what the earlier lectures showed you, that a deterministic optimization approach requires the forward equations and the backward or adjoint equations. So that's the mathematical part of it. The engineering part of it is this, the presence of this point over here, which tells you that yes, there is a minimum critical mass over here, which happens at this combination. Okay, so that's the conclusion that we get from here. Okay, now let's go. Okay, I think let's stop over here. That's enough for today's lecture. Now, in the next lecture, I'm going to look at non-multiplying systems. So the next lecture, which will be lecture 27, I'm going to do with you two non-multiplying systems, one a radiation shield and the other an explosives detection system. So, okay, so let's stop over here.